This video is an introduction into reactions of substituents on benzene. A substituent on benzene ring can undergo one of the three general types of reactions. And those would be, first, reaction of the substituent itself. So in those reactions, benzene ring is unchanged, but benzene ring may affect the reaction outcome and reaction rate. Important feature of these reactions is that benzene substituent bond is not broken. So here is in general terms, reaction occurs on the substituent, and so substituent on the ring is converted to a different substituent, but bond to the ring is not broken. An example would be a reaction of benzyl chloride with, let's say, ethanol at room temperature. Product is benzyl ethyl ether, and byproduct is molecule of hydrogen chloride. So in that case, chlorine group has been replaced with a toxic group, but benzene ring itself is unchanged and carbon-carbon bond is not broken. In the second case, and those are the most common reactions, the most numerous reactions of substitute benzenes, reaction is on the benzene ring itself. Substituent is unchanged, but substituent now may affect the reaction outcome, and benzene substituent bond is not broken. So those are common examples where reaction occurs somewhere else in the ring and one of the hydrogens, one of the protons on the ring is replaced by another substituent. So an example would be bromination of nitrobenzene. We'll cover that later in more detail, this particular reaction. So bromination of nitrobenzene gives a meta-bromo-nitrobenzene as reaction product. And the nitro substituent is unchanged, even though it does affect reaction outcome. Finally, third type is also reaction on the substituent, but it's a substitution reaction of the substituent. So a substituent is replaced by another substituent, while benzene ring is unchanged. And in this reaction, unlike first type of reactions, benzene substituent bond is broken in the course of the reaction. And so, as you can see, in general terms, substituent Z is replaced by a different substituent Y. So carbon Z bond is broken and carbon Y bond is formed. An example would be a reaction of diazonium salt. Here we have in the second row example of diazonium salt. Reaction with potassium iodide gives iodobenzene. So carbon-nitrogen bond is broken, carbon-iodine bond is formed. Or another example is substitution reaction of chlorobenzene under these described conditions. So solution of potassium amide in ammonia, liquid ammonia. And in this case, we have benzyne type reaction, something we'll cover much later in this course. But carbon-chlorine bond is broken and replaced with carbon-nitrogen bond. So chloro substituent is replaced with an amino substituent. In the rest of this video, we'll examine the first type of reaction. And that's reaction on the substituent itself, where benzene ring substituent bond is not broken, benzene ring is unchanged, and reaction occurs on the substituent itself. Some of it will be summary or review of reactions we have covered already in different chapters. For example, reactions of alkyl substituents, such as free radical halogenation, proceed readily on benzyl compounds. Basically, if benzene ring is substituent in benzylic position, and this is something we have covered already. The reagent could be something like bromine or halogen in general, like bromine or chlorine, or N-bromosuccinimide for bromination or N-chlorosuccinimide for chlorination. Reaction occurs only in benzylic position, that means on the carbon directly attached to benzene ring, because benzylic radical is much more stable compared to any other radical that could possibly form in the course of these reactions. The reaction is rather selective and occurs only in benzylic position. If there is more than one benzylic position available, as this compound is called tetraline. It has 4 benzylic protons, so all 4 could be replaced by using an excess of bromine. Another common reaction is benzylic substitution, and that's also a review. That's an SN2 reaction, and you may recall that benzylic compounds readily undergo SN2 reactions because neighboring benzene ring stabilizes transition state, makes this reaction favorable and rather fast. So reaction occurs under mild conditions. Actually, even SN1 reactions occur. These are a couple of examples of SN1 reactions because benzylic cation is rather stable. So SN1 reactions also readily occur benzylic compounds like benzyl bromide in the first example and benzyl chloride in the second example. And here are more numerous examples of SN2 reactions. You may have noticed that we can prepare benzylic bromide in free radical substitution from an alkyl benzene. And so that benzylic bromide could be converted into a wide variety of different compounds by carrying out functional group interconversion in an SN2 reaction, in an SN2 substitution. If you wish, you can pause the video here and examine this diagram in more detail to see all the variety of reactions that can be carried out on this compound. Alkyl substituents on benzene ring are readily oxidized. Typical oxidation agent is permanganate, and carbon atom directly attached to benzene ring is typically oxidized all the way to carboxylic acid. So regardless of what is the alkyl group that is attached to benzene ring, it always ends up as being carboxylic acid. And in the past it was used to determine how many substituents are on the benzene ring and what is their relative relationship. Are they orthometapath apart to each other, or if it's tri or tetrasubstitute benzene, is it 1,3,4 or a substitution pattern, or 1,3,5, 1,2,4, or whatever pattern is. And that could have been easily determined from melting point of the corresponding acid, because all of them have different melting points, and all those, of course, carboxylic acids were known, and their melting points were available in tables. As you can see, we cannot determine what was the original substituent, only what was its position, whether benzene was mono or disubstitute, as in this case. And you can see that two metasubstitute benzenes give the same product, or two monosubstitute benzenes also give the same product. One limitation to this method is that carbon atom attached to benzene ring must have at least one proton to be oxidized. So quaternary carbon atom does not undergo oxidation. That means tertiary alkyl substituent attached to benzene ring does not undergo oxidation. And that was also used as diagnostic test for tertiary alkyl group attached to benzene ring. Also, benzylic alcohols could be readily oxidized. With permanganate, they are oxidized just like alkyl chains, carboxylic acid. But if we want to oxidize alcohol to carbonyl group to corresponding ketone, then we will use manganese dioxide, much milder oxidizing agent. So note this difference. Mild oxidizing agent, manganese dioxide, oxidizes benzylic alcohol to corresponding benzylic ketone, while permanganate oxidizes it to benzoic acid. And finally, alkyl substituent. Upon oxidation with Jones reagent, I hope you remember Jones reagent, solution of chromium trioxide in concentrated sulfuric acid. So upon oxidation with Jones reagent undergoes benzylic oxidation, oxidation of benzylic carbon, and that carbon is oxidized to carbonyl group. So this is another way to make phenyl ketones. Alkene substituents on benzene ring can be readily reduced under catalytic hydrogenation conditions. So typical catalytic hydrogenation reagent that is not very vigorous, such as nickel, reduces alkene side chain, but does not affect benzene ring. So in this case, benzene ring could be left intact. Under more vigorous conditions, we can accomplish also reduction of benzene ring. More vigorous conditions involve either use of nickel catalyst at high temperature and high pressure of hydrogen, or use of mixture of rhodium and platinum catalyst in ethanol. That is much more vigorous catalyst and will reduce benzene ring even at room temperature. Addition also readily occurs to alkene substituents, and addition is regioselective. Addition occurs in such a way that electrophile is added to carbon away from benzylic carbon, so that benzylic carbocation can be formed. Benzyl carbocations are very stable, and so for that reason, for example, hydrogen bromide adds in such a way that proton adds to carbon of the double bond that is away from the benzene ring. That results in formation of more stable benzylic carbocation, and then that carbocation reacts with nucleophile, with bromide anion, to give corresponding benzylic bromide. In the presence of peroxides, of course, regioselectivity is opposite, because addition of bromine occurs first, and that gives more stable benzylic free radical, which then combines with hydrogen to give corresponding product. Another substituent on benzene ring that can be readily reduced is Nitro substituent. One method to do it is catalytic hydrogenation. So reduction of nitro group with hydrogen in presence of nickel as a catalyst results in formation of corresponding amino group. So that's a way to reduce nitrobenzene to aniline. That's the way we would carry out reaction in industry, and aniline is important industrial intermediate. In laboratory, we would probably use somewhat different method, probably something like Clemmensen reduction. That means use of tin or zinc in hydrochloric acid. That reduces nitro group to amino group, but because conditions are acidic, we end up with corresponding ammonium hydrochloride. So the product has to be treated with sodium hydroxide or some other base to release aniline. If there are two nitro groups present in benzene ring, of course, using one of the two above methods, we could reduce both nitro groups to amino groups. But if we want to reduce only one nitro group to amino and leave the other one intact, then we should use ammonium sulfide. Ammonium sulfide reduces only one group, and the reason why it reduces only one nitro group and not the other is that ammonium sulfide does not affect unactivated nitro groups, and nitro group is activated towards reduction by ammonium sulfide by presence of another electron withdrawing group on the ring. So when there are two nitro groups present on benzene ring, one acts as electron withdrawing group and activates the other nitro group. Once that other nitro group is reduced, that nitro group is now electron donating group and does not activate remaining nitro group, and that's where the reaction stops. And this completes our review of reactions of substituents on benzene ring, and next we are going to look at substituent effects on reactions of benzene ring.